I'm Joao. Um, I basically run network systems at Fastly. We don't really do titles. We're too small for that, or were historically. But essentially what I do is make sure we design and run the network as best that we can, and we do it mostly through software. So Fastly, you might not have heard of us, but you probably inadvertently use us all the time. Like whether you push code or download code or procrastinate, like you are inadvertently retrieving content from our servers, right? And basically we're a CDN, right? And content delivery network is essentially like a large distributed cache system where you have different points of presence around the world. And as a user, by resolving the DNS name, you are directed to our closest POP. If we have the content, we immediately deliver it to you. Otherwise, we go back to our customer's origin to retrieve the content and we cache it, right? This is not rocket science. CDNs have been around for a long time. They just happen to mostly be terrible. What I'm going to talk about today, so I'm not really an SRE, I kind of am, but everything's murky in startup world. So I noticed that lots of people use this word, right? And it means inherently different things. Scalability is all about the dimensions you are scaling along, right? And one thing that I noticed with scalability talks is that usually you're presented with this massive system, which is so big it starts to get kind of fuzzy around the edges, right? Think of a system as large as Facebook or Amazon or Google, right? That's proper large, right? And the dimensions talks normally come across are what happens when you're at the boundaries of knowledge, right? When you don't know how to scale further because we've never actually encountered this before, right? And academia comes from this kind of aspect. Amazon, Google, Microsoft, these guys all have research departments dedicated to figuring this stuff out, right? And those are good talks on scalability. There's also a technological aspect, right? I normally put hardware in this, like new developments in manufacturing process. Things are getting cheaper, 100 gigabit Ethernet. That changes everything, right? And you can scale a lot better with those properties. A lot of talks kind of focus on that as well. And then there's complexity management, right? The overhead of running such a big organization, coordination becomes an issue. Even in Pedro's talk, what title you give a job becomes an issue at that scale, right? And there were interesting talks on this as well, how do you run a team of 200 SREs, right? Challenging stuff. I would argue that almost everyone is actually not there. They're somewhere to the side. And they work on systems of completely different scale, right? Which seems insignificant compared to the scale at which the big guys operate at, right? But it's just scaling at a different dimension, right? So the constraints here are very, very different. If you're in a small company, in particular startups, everything is different. The first constraint you have is time. I can't trade off reliability today for amazing reliability in a year's time, because when you're a startup, nothing actually guarantees you'll be around in a year's time, especially if your reliability is shit, right? There's also the question of money. Money is a scarce resource. And the whole point of startups is to prove that you can actually evolve a product with better capital efficiency than all your competitors and all the incumbents, right? And finally, people. Hiring is notoriously hard. How do you build something that scales when you don't have people, or it's hard to attract the right people? And also, hiring people costs you time and money, both of which we've established you don't actually have. And the other thing about people is it's very hard to tell whether someone is competent and productive in a startup environment, because you can come into a startup with a completely closed mind frame as to how to solve a problem, right? And it's kind of impossible in the hiring process to figure this out. In the meantime, you're growing, and everything in comparison is a huge challenge, right? You can get DDoS out of existence very easily by a script kiddie if you're really, really small, right? But it's not just DDoSes, it's not just attacks, right? Getting a new customer can be such an increase in traffic relatively that it can obliterate you. And also, if you're in a startup where a lot of your selling point is configurability and being flexible and being an integral part of your customer's infrastructure, your customers can actually blow you away just by configuring something in an unexpected manner, right? That's a big thing of us. If you're a customer of ours, you can configure VCL. You can actually program how the caches compute stuff at the edge, right? Which is huge, but it's also like a potential liability, right? So this talk is kind of about how Fastly became a multi-terabit network. At some point in 2014, we crossed the 2 terabit per second mark in global capacity. We had around 20 POPs. We had around 2,000 individual BGP announcements. And we were dealing in like 1 million requests per second, right? And from the network side of things, we had 2 network engineers from an operational level. This is a magical number because it's the smallest number you can have an on-call rota with. And we had me writing all the network software, right? So somehow, this talk is about scalability, but on these specific dimensions. Like, it's just observations on network scalability from a company that used to be a startup. We are no longer a startup. Like, we have a lawyer now. It's just like... So, first point. Anything you don't explicitly control is an implicit liability, right? And I see lots of people do mistakes where they kind of give up control at the very beginning of the company in terms of their architecture and design, and they don't realize what the ramifications are later on, right? And so say you have the internet. People normally draw this as a cloud, but like this depiction is just as accurate as far as I can tell. And from the internet, traffic comes in to your point of presence, right? And you can conceptually imagine a POP as just this router that connects to caches, right? This is what our kind of initial architecture kind of looked like when POPs were smaller, right? A question that everyone has to solve if they have this kind of infrastructure. How do you load balance traffic? And above all, how do you gracefully fail over if a server fails, right? These are 2 problems that are not just us. These are transversal. And you can think of it at different levels. You have application layer load balancing, right? You have TCP level load balancing. It's just a general kind of computer science problem. Okay, so one solution is use DNS, right? Really simple. You have different entries, you weight them equally, and for example, if you want to remove cache A from rotation, you just remove the weights or change the weights, whatever, and DNS will be round robining via the other servers, right? This is a pretty bad idea. It gets really hard to manage as the number of hosts actually increases because you're doing lots of DNS updates all the time, especially if you're constantly removing servers from and into production. I would claim that you probably do this way more often in a startup because you're still fixing lots of bugs and you're still trying to find a product fit, for example. And you also have less infrastructure, so the impact of removing something from production when you have almost no infrastructure is massive, right? It also goes against the system's principle of doing one thing and doing it well. Like, we already use DNS to do redirection to the closest POP. If we started to embed the logic of what server it has to go to as well, it becomes very hard to actually decouple this efficiently. But the biggest thing, you don't control DNS TTL, right? The people who have to respect DNS TTL might not do, right? So, like, one of the biggest French ISPs will not accept a TTL under 30 minutes. Think of that when you do a production service which relies on DNS redirection at a lower granularity, right? Yeah, so that sucks. Another solution is buy a load balancer, right? This fixes everything. It's nice. Connection terminates at the load balancing box. Load balancer demultiplexes requests across your backends. Problem solved. The problem is economics. Because basically you have this very nasty relationship between the amount of state you can keep and how much it costs to actually maintain, right? And so, say you're a startup, and you know what your existing demand is, kind of, because you can like check the graphs, see how many flows you actually have. Then you might actually, well, know what the projected demand is, kind of, and like add a bit of overhead, and then kind of invest in a load balancing box, which is kind of around that, right? Everything outside that is completely out of your control, right? So if you buy these boxes and a year from now you have 2 times more traffic than you had originally expected, you have like very expensive paperweights you can't put anywhere in your architecture, right? Huge cost. And in general, you shouldn't do load balancing, especially if you're serving at the edge, because flows are exogenous to your system. You don't get to choose how much demand you actually have. You don't actually control DDoS, right? Like, these are things you don't control. And so the solution is crap, completely, in this context, right? So what most of the industry has kind of like consolidated around in terms of architecture is using ECMP. So ECMP is basically a capability, in a sense, where you can have multiple routing entries for the same destination prefix with different next hops. And so here you have like 4 entries for the same destination network, each pointing at a different server, right? And if your flow comes in, it will get hashed consistently onto the same entry. And so in this case, the flow comes in, it gets hashed onto server B, and that's where all the traffic in that flow ends up, right? Because all the flows will share the same 5 tuple, right? This is great until you remove server A from rotation. And in that case, your routing table is going to change. And what it ends up doing is ends up rehashing connections. And so the server that was previously hashing onto B might now be hashing onto server C, which kind of sucks because both B and C were always in rotation all that time, right? So you don't actually control rehashing. And actually nowadays you can get it. Now 2015, you're starting to see vendors which have a consistent hashing mechanism for this to avoid rehashing. But this was a problem we were facing like 2 years ago, 3 years ago, right? Like, you don't control vendor roadmaps, right? You can ask them to do stuff, but you can't make it go faster, and you're still stuck with the hardware you already have, right? So this is a problem. And this is kind of like the least optimistic talk so far because I basically have said everything sucks. But a big problem in networking is most people kind of resign themselves to what they have too soon, especially if you come from a point where load balancers are crap. ECMP is so much better. That is pretty much true, but ECMP still sucks. And no one actually tries to think what the next step might be, right? It's really irritating. So what we come up with is something internally we call failD. Out of curiosity, does anyone know OpenFlow here? Everyone heard of OpenFlow? Yeah, fuck that shit. Learn IP tables. Learn IP tables, guys. So still same thing, ECMP, right? ECMP has the correct behavior with a nasty like particularity, right? So what we do instead is you do a routing table, but you insert as many ECMP entries as you can to the same destination network. And what you do is you make up next hops, right? Nothing says you have to have a next hop that actually exists anywhere in your network, right? And somehow you embed information into that next hop as to what you would actually like it to end up, right? So in this case, like obviously fake IP address, as you can tell from the letter. But the idea is you could actually embed multiple next hop entries which somehow all go to A, or at least intended to go to A. And you do nothing else with the routing table because you don't control rehashing. You just maintain a fixed routing table all the time, right? What you do manipulate is the ARP table, right? And the nice thing here is you have the same flexibility of ECMP, but with none of the rehashing. You get to decide where traffic ends up in your network. Again, not a valid MAC address. Don't try this at home. But somehow in the MAC address, you can make up MAC addresses as well. This is great. So the MAC addresses we use kind of embed 2 pieces of information, which is where the, like, first off, what host you actually want it to point at. So that MAC address, AA, just tells us we want to go to server A, right? And this is cool. Flow comes in, you get hashed to the first route entry, and then ARP points you at the right server, right? Now this happens. You want to drain a host, right? This is interesting. A somehow signals to a controller on the switch that it wants to be removed from service. Or it might have timed out, but that's not as graceful anyway. So let's just imagine A requests to be removed from the pool. You're still getting hashed into the same entry at the routing table. What you change is the ARP entries, right? And in this case, it's interesting because each of those entries gets changed to something subtly different. In this case, for example, 10.1.a.1 goes to BA. And what that encodes is you're now going to B, but you used to belong to A. right? Now the nice thing is, at the server, not using OpenFlow, you can actually redirect traffic that doesn't exist locally back to the old server, right? And so B starts getting all the new traffic, but all the old traffic still goes to A, right? And to do this, you have to incur some amount of state in server B, but that's fine. And then after some time, you just quit. Like, if connections are going to last that long, it's probably because they're hanging or something is wrong anyway, especially when you deal with small objects mostly. So here, same thing. After a while, you change the MAC addresses again to just point at server B. And now there's no more connection redirection. It's just, if anything was still standing, you'll just reset it. And so what this means conceptually is that, well, imagine you're draining a host, right? Like, you have a set of active flows which are still on that server when you take it from production. What ECMP gave you was that all those servers die, right? Which kind of sucks. What a load balancer gave you was that all of those servers will live, but you will die by state explosion anyway, because you have a vulnerability. Like, you're basically exposed to DDoS attacks, right? And that sucks. What we kind of came up with was interesting, because we control the trade-off depending on how much cutoff time we are willing to expend, right? We have this draining time, which up until the point where we decide to finish draining, we are incurring state within our servers. But we managed to actually save most of the active flows which were still going, right? And this is huge, especially when you're small. Like, the cost of taking stuff out of production is not the same when you have 10,000 servers compared to when you have like 4 in a POP, right? And we're also in an industry where, like, if you're in a business-to-business kind of company, you're expected to be more reliable than the incumbent, right? Like, it's a huge difference in concept. So yeah, this is a generalization if you think about it, right? Because the market somehow only ever gave us the 2 ends of the spectrum, right? And so if we decide to lower the draining time, we approach something that looks like ECMP. If we decide to increase it, we go towards something that is more like a load balancer, right? And that's cool. This is kind of part of the lesson of that, right? Yeah, if you're in a startup, be very careful of what you invest in. So for example, the load balancer example is classic, right? If you need a load balancer, you could do worse than picking a big IP 10350 or whatever. Actually, I'm joking. You can't do worse than that. But like, you don't just lose dignity by buying these. Turns out, $200,000. That's list price, guys, or close about. You might get a discount. And yeah, like, the value we were willing to pay for that was closer to 0. And to be honest, if I got it to 0, we would have probably pivoted the business and started selling these on eBay. That's how, wow. So some people think they need load balancers, and that's not exactly true, right? Like, you need load balancing. These are completely different concepts, right? Load balancer is just an appliance which happens to provide load balancing, right? What we ended up doing then was kind of building a distributed load balancing system, right? And this is how you essentially save a lot of money, but you actually end up with something way better than what you would have started with anyway, right? And so that's cool, because now to build a point of presence, things become easier, right? You have 2 providers. I'm pretty sure that's what they look like in the wild. And you buy a router, and you get a BGP table from each provider, you install it into the FIB, and you use serve as the default gateway out. This is pretty much, conceptually, this is what, like, at the most core level, this is what a POP should look like, right? Except routers aren't very cheap either. Like, great box, Juniper MX 960, right? Does all it says on the box. Really fucking expensive. Like, if you start putting the line cards and counting the optics, you come to $500,000, right? This is what everyone, as far as I can tell, does in the industry, right? Like, they think they need a router. They don't. They need routing. Like, a router is just an appliance which provides routing, like, and no one seems to care, right? So what we essentially did was we built distributed routing, right? Sounds simple enough. And we did it by just buying a ton of these. They're workhorses. Like, They have their limitations because they're switches, but they're actually highly flexible. They have a decent API, and you can get away with a lot by just not using routers at all, right? List price, not even in the same ballpark. So don't know why people are even thinking of routers unless they really need them. So what a fastly pop actually looks like is you buy a ton of switches, you run a user space BGP daemon on the switch to receive the tables from the providers. You reflect BGP down to the servers because you don't have a fib on the switch which can actually take that many routes, right? And then you kind of just use a BGP daemon on the server to inject multipath routes into the fib, right? And that's kind of cool. You still have to do some tricks to pull this off. Basically, the switches and the servers are all part of the same distributed system, but we know how to build these. We've been doing this for decades now. So somehow the switches have to emit the next hop IP and MAC address down to the servers so that the servers can actually configure like a point-to-point link and an ARP entry, because the provider and the server technically shouldn't be in the same L2 domain, and you can't actually ARP for that. And then you just send directly to the provider next hop, right? So what you end up with is a system where the server is actually offloading all the traffic directly onto the provider, right? And so if you go into one of our caches, like literally we're running like 2 million routes on each of those boxes. And the boxes are fine because the money we save on routers, we can actually beef up all the actual servers. And I'm much more confident about the fundamentals of how this works with time, because servers will improve. You won't gain that much more flexibility out of your hardware in the long run, right? So this is what a POP looks like. It's just a bunch of servers and a bunch of switches. It's not supposed to be complicated, especially when you start out, right? From the investor perspective, however, very different, because we're saving a lot more money per POP going forward, right? And we can actually use this in other aspects of our business, right? Whether it's actually investing in performance in terms of bandwidth. Oh, okay, that's fine. In terms of bandwidth, or just using better servers, or just fleshing everything out with SSDs, right? So there are trade-offs there, and no one does those trade-offs because they don't realize they can get rid of a huge part of the cost with running infrastructure. And they don't do that because they don't actually think from a systems perspective, fundamentally, right? Cool. Another big part of it, like, it's not enough to actually just do software to run the systems in an autonomous fashion, right? You have to actually think about the people who are managing these systems. And generally, it's a lot easier to make people less busy, just by looking at where they spend their time. And I kind of think about this in a parallel to like the DVD market. So for those of you who are too young, there used to be these things called DVDs. And there was kind of this other thing called the internet. Turns out people were getting movies from the internet a lot more than they were from DVDs. And the people who were selling DVDs did the perfect rational thing, which was reduce the utility of their product even more by preloading them with these shitty adverts, right? Saying that you wouldn't download a car and trying to make you feel guilty, right? That you actually, and like everyone else was like, no, I totally would, right? Like, doesn't even make sense, right? And yet, like, if you think about like what's happened to how different software development is, it might not all be better, but it's all quite different, right? The iterations, like how we do development, how we do deployment, so much has changed. Like everything is APIs, and you have all these beautiful things built on Git and stuff like that. And really, like, the networking industry has always been like, yeah, but you wouldn't do that to a switch, or you wouldn't do that to a router, right? Like, it makes no sense. And historically, like, my perspective of networking vendors has always been like, yeah, you don't do this because networking is hard, right? And they come up with lots of excuses traditionally, right? Like, well, there are resource constraints. Respect that. Like, most switches and routers are closer to like embedded devices than they are to our servers. When you look at the resources, but yeah, like you won't run Chef on them necessarily because that's just a hog. There's other stuff like protocol standards, right? There's interoperability issues. Like, if we give you too much power, you might destroy stuff, which is the most pedantic thing you can actually do, right? There's also security concerns, right? Like that somehow if you manage to change it, you might break some assumption and like no one cares. we've gone past that model in software ages ago, right? And so the one thing network vendors never acknowledged was a problem was network vendors, right? Like, really hard to imagine that. So looking at the life of a network engineer, kind of opsy thing, right? Where is time spent needlessly? Like, what are the day-to-day activities? A lot of it cannot actually ever be automated away, because a lot of it is also interfacing with the physical world. A lot of it is interfacing with providers. There's stuff you just can't give away. But a lot of other stuff is kind of, well, simple, right? Like, spend a lot of time pinpointing path failures, right? Because some distributed system comes up, starts alerting, something's wrong. And every application developer ever just assumes, like, you pump data down a socket and it comes out the other side, right? Like, sure. We kind of solved that architecturally, right? Because by pushing routing down to the servers, we can actually get to probe every single path individually, right? So we have a tool called stping, where if you just ping it, it will ping via all of our providers. And you can immediately see if something is broken. You can also see here that, like, this is an Anycast address, obviously, and via Telia it takes 25 seconds. Via L3 and Cogent, it takes less than, like, 1 millisecond, right? Doesn't really matter for us because we don't use that address. That's just an example. But what else do you waste time on? Well, if something is broken, you're going to have to change it, right? And the world of changing routes on a router or a switch is some arcane configuration thing, right? Like, the chances of you getting it wrong are spectacular. So how do you change preferences manually on our infrastructure? So it turns out we write a lot of software on our aristas. Aristas provide APIs to, like, plug into different parts of the system. You can actually do your own command line interface if you want. We do something slightly simpler because it was easier to get through, and it's really intuitive for network ops to kind of use. Really simple. You enter the configuration. Then you use an upstream alias to directly, like, shortcut to the interface you're actually supposed to be operating on, right? Here, you just write L3. Very hard to misspell L3, very hard. The description field is actually populated automatically by the switch controller. So it gives you actually usable information. Remember, we're using a user space BGP daemon, so that won't actually plug into the command line interface automatically. So what it says here is, like, these are the announced prefixes. Names, not addresses. Very useful, right? Some of these prefixes might actually map to multiple BGP announcements, but it doesn't matter. Conceptually, you're always operating over named prefixes, right? And it also gives you, like, live BGP info of what's actually happening in the daemon. So there's no, like, going into the daemon, rewriting a config file, reconfiguring. None of that crap, okay? How do you actually change a preference? Well, you can just pass a very simple, like, syntax through the description field. So literally, to increase the Google local pref on this interface, you actually just pass plus and the ASN number, and it kind of immediately flips it around. The nice thing is, this gets propagated immediately down to the servers, and now you're using L3 to reach Google, right? The amount of steps this normally requires traditionally is insane, and that's because most vendors never gave a shit, right? Like, they just never really cared about how people actually use the systems. They would rather sell certification as if that somehow means you understand networking. Like, it doesn't. Another thing, changing prefix announcements, right? Sometimes you actually have to remove an announcement from service. Especially Anycast, if you're manipulating Anycast, sometimes there's just local problems. You have to just withdraw the prefix. Or you might want to force traffic onto a specific ingress in your POP. So how do you do this? Well, you just tell it to withdraw all the HTTP Anycast prefixes, right? And it's really simple notation. Like, this is something you do really regularly. And you should always start to try to figure out how to do this manually and reduce the, like, surface area for errors, basically. And again, like, pretty much immediately updates the BGP session status because you have a controller which is, like, asynchronously reacting to all these events underneath, which does all the hard work. And so basically we created an interface which is stable towards the operator, but over time the amount of things that is involved going under this has completely changed, right? And remember, we have a distributed system for routing, so pulling a route is no longer as simple as just removing an announcement for BGP. You actually have to pass that information down to servers, right? So all the complexity actually remains hidden, right? Yeah, another thing you do a lot is changing global routing policy. And this is kind of important. We generate lots of BGP announcements. We have lots of transit providers. We have lots of IP ranges. We have IP ranges with different kind of communities, because Anycast, for example, you might actually have to constrain where they go in the network. Like doing this manually is hard. It was kind of a thing when we still had like 6, 7 POPs. But it gets very cumbersome. It's something that is actually essential for performance, right? Manipulating your inbound policies ends up dictating how much latency you're actually going to get, right? That's the difference between you ending up in Sydney when you're actually in LAX, right? And that sucks. Especially as you get more into peering, this problem gets more and more complex. And also changing policy per device. It takes a long time, that's true, but whilst you're changing, you have to remember that your network becomes in an inconsistent state. And that can have huge implications where if you're withdrawing a route, for example, your traffic to that prefix starts getting funneled into less and less POPs or less and less switches, right? And so there's actually a very real risk here of saturating an inbound, for example, just because you make a single mistake, right? What we end up doing is actually we logically centralize all of our policy, right? That's like one single route server, but it's actually another distributed system. It's just a set of route servers. It's not meant to be complicated. But the important thing is you always try to logically centralize things so that you reduce the surface error for mistakes, right? And so to actually control this, we have an entire workflow based around GitHub, right? We are probably the only people I know that deploy BGP changes worldwide via GitHub. Like at its base, at its core, it's just Git, right? So if GitHub has problems, this is fine. This all works anyway. But yeah, no one actually bothers to think of how to do these things properly unless they're a really large scale. Like there is actually a surprisingly little amount of entities which try to fix networking problems at a scale other than Google and Amazon. Like, it's just insane. And it's not even complicated to provide a huge value-added service because there's a ton of people who do this wrong. All right. So what you do in the workflow is you stage a policy a policy file, right? You just edit the policy file, you stage it, then something like there's a hook, and this hook will end up calculating all the exported routes for you and uploading the diff, basically, right? And what you see in the pull request normally is not only the reason you're doing this change, you also see exactly what switches this change is going to affect and what the BGP community diff is, right? And then we have everything peer-reviewed because this is a huge complexity problem when you get to this level because everything at the network level is like numbers and stuff that humans can't possibly comprehend. And network engineers, especially traditionally, like we have a tendency to not actually acknowledge the amount of complexity we're dealing with on a daily basis. And then you just get to a point where you just can't handle it anymore. And by then it's too late. You can't actually fix this problem, right? And this is actually, so BGP policy for inbound is actually something I don't believe will be automated anytime soon, like fully automated. Because it's such a complex layer of politics and economics involved that it's inherently hard and it's inherently unstable as well. So I'm not sure we'll ever get it to the time scale where anything useful can actually come of it other than instability, which is kind of useful sometimes. But some of these differences is like, if you look at this policy file, this was a policy change, by the way, because L3 had some fiber optic cut kind of thing, and we had to remove Anycast from Europe. And if you remove Anycast from Europe, all of your L3 traffic is going to get hauled into the US, and then your latency numbers crap out. So you don't want that. So all we have to do in the configuration file is just write no export. But if you get that line of code in the wrong stanza, you will end up withdrawing the entirety of Fastly from the internet, right? And the main, like, the core reaction of most people when they see that kind of responsibility is to not do it. Like, never place that much responsibility on a single system, right? And that's kind of the complete wrong intuition. So it's hard to automate, but like, you should just make sure that people can get it right. And you do this by applying all the same principles you do in software to all the crap you do in networking, right? It's not supposed to be hard. And a lot of these tricks were so simple. Like, they really didn't require much of my time. They just required like understanding where we were wasting time. But it reduced the amount of time we actually exert in operations dramatically, right? Like, literally 3 people was all it took until early 2014 to run like a 2 terabit network, right? And that's like, that's probably less people than most people here will have reviewing their expenses. It's just ridiculous, right? Reduce human error dramatically. Like, it's really hard to comprehend. The CDN industry has an incumbent, essentially, which is Akamai, right? It's really, really hard to steal customers from Akamai if any part of your system is worse, right? Because there's a natural inertia from most of these companies because they're already on there, right? So if you're going after that business, you are screwed if your reliability numbers ever go down. Another really important thing about all these tricks, it allowed us to actually lower the barrier of entry for being a NetOps, right? Like, we have people on our data center team who can now actually have like transitioned into the NetEng role because they can start doing it very, very easily, right? We don't need a NOC. We have people that can actually run everything. And the really nice thing is the Arista eAPI, you can actually interact with Arista devices in a RESTful way, right? So those description changes, actually, you can just do that via HTTP anyway. And so you end up with an instant RESTful orchestration layer. And so now you can start building, and we start building software to actually manipulate AS preferences, for example. This isn't supposed to be hard as well, right? Like, but you can do it slowly, and you can do it by bits. But the first bit you have to actually solve is the human element, right? Because if people can't reason about the network they're running, no software will actually fix that for you, right? And in general, like, the main thing about Fastly is that, yeah, we actually ignored a lot of conventional wisdom, right? And this is really important because if you're a startup, by definition, best practices were set by the very people you're supposed to be the antithesis of, right? You shouldn't actually strive to be like them. Otherwise, you'll end up being like them, but with a smaller market share, and that sucks. And most of this was done via just, first off, saving money. Capital efficiency is like really important as you scale. And if you manage to actually prove the worth of your product and maintain capital efficiency, you are golden. You're on the home stretch there. And we did it mostly by thinking of this, everything is a systems problem, right? And not having a preconceived notion of what people were selling us was the actual solution. It's just a tool, right? And at our level, at least, like, efficiency really matters. We strive a lot, like, we don't actually want equipment. We want to avoid having more people than we should. And lots of people, when they're early on, when they start seeing themselves overwhelmed by work, they actually have the complete opposite reaction, right? They start hiring people left and right, and then they figure out those were actually not the people they wanted in the first place, right? We also like saving time. A lot of it is just purely design, purely architecture, right? The fact we pushed routing out of routers and onto servers was hugely valuable. And arguably, it's a more strict interpretation of the end-to-end principle than anything else, right? Because now routing is at the application, practically. And then you can start doing really cool things at the application, right? You can send HTTP headers, which basically select your egress. That's hugely valuable, especially if you surface it up to customers at some point, right? Also, reducing the cognitive overhead, always thinking about what is it that you actually want to do, and having something else translate what that actually means within the network, right? And again, like, there's a very natural reaction as an engineer to try to solve things completely, and to the point where everything is fully automated. And we kind of did that with the load balancing solution. Everything is completely automated, but it's not always possible, right? You should always try to fix the ops side of things first before you move on to that. And in general, so not only be wary of best practices. be wary of cool stuff, right? Like, you should be trying to build cool stuff, not necessarily building on cool stuff, because that's where a lot of your uncertainty comes from, right? You're using new technologies in new ways, and that's my main problem with OpenFlow kind of thing. It's probably, you are banking on a lot if you're expecting OpenFlow to get to the point where you need it to be within a short period of time, right? You don't want to, like, you want to cut your uncertainty as much as possible. And like cool stuff is what ends up getting you like an OpenFlow controller written in Julia with a MongoDB backend or something like that, right? And then they say it's web scale, and then it craps out the first thing you try, right? And we have this problem as well. Like, it almost makes us, sometimes it almost has the unsexy thing, because like a lot of Fastly initially was written in Perl, which everyone likes to make fun of, myself included. But it works, and there's intrinsic value in that. And there's a lot of value in having all of the founding team know a hell of a lot about Perl, right? There's no like, oh, well, how do you do this in Go? No one's done it before. Oh, crap. And like, don't try to be perfect, at least right off. Like, once you figure out what your product actually is and where the demand is, you'll have plenty of time once you've validated the entire business model to get it perfect. And it turns out to actually compete, you very rarely have to be perfect unless you're trying to do the exact same thing. A lot of this was making, like in the initial phase, a lot of it was making sure that you didn't design yourself into the same corner everyone else is in, right? You don't want to end up there because that's just a bad business choice in the long run. And with that, I'm pretty much done. We're hiring in case anyone's interested. That was pretty much it. Questions? Thank you. Is there a microphone?
Okay, I'll just.
Yeah, I can repeat the question if you want.
How much of the things you discussed are covered by the open source Failed project, and how much are?
Oh, it's not open source. Yeah. So it's more like patent pending, like the opposite of open source, I guess. Yeah, I shouldn't have gone into too many details there. Yeah. Oh well. Shit, I have a lawyer now. I forgot. Yeah. Any other questions? Sorry?
Is the symbolic stuff that I saw, the desk not HTTP, was that all built into it, or is that something else?
Oh, yeah, so basically we just built a command line interface over the actual command line interface. So you're passing a description field. You're interacting through the description field, essentially. The main reason for that is like it's more easy to just plug into the eAPI and that exposes it. It's also more portable if you think about it. Like, you expect most routers and most switches to have a description field. A lot of the other features are still not fully commoditized in this space. Yeah, so.